All right, let's do this. We actually just have a fairly quick lecture to close out our new stuff that we learned how to do, new stuff that we are going to learn how to do. And then we're going to spend some time just reviewing what it was that we learned over the past few weeks, because the past few weeks were a little dense, right? We learned about a bunch of different chemical reactions, so we're just going to kind of take a minute and summarize that. All right? We got a little bit of new stuff to cover. This relates back to a topic we've discussed previously, concentrations. All right, but now we're going to talk about units that are used outside of chemistry to refer to concentration. All right, and that's not to say you'll never see these in chemistry as well, but again, typically in chemistry, we like what units for our concentrations? Molarity, right? And that's because chemists love moles. You saw how molarity plugs really nicely into our stoichiometry, into our math of chemical reactions. Anytime you're doing math with a chemical reaction, you need to be in units of moles. So that's why molarity is very, very convenient for chemists. Also, think about the lab. How many different ways do we have to measure out volumes, to transfer certain volumes, right? We like working with volumes in the chemistry lab as well. So both of those two units kind of marry together to make our units of molarity. All right? But chemists are the only science discipline that give a crap about moles. All right? Nobody else really cares about moles because nobody else is really keeping track of how much of a chemical reaction happens. But there are plenty of other branches in STEM that need to use solutions and need to talk about how much solute there is in those solutions. So for example, the medical field. A lot of drugs are delivered in solution. You know, you just imagine like your TV picture of a hospital. They're giving injections, there's IV drips, all that sort of stuff. Well, what they're doing is they're delivering a certain amount of medicine. And a 95-pound female is going to require less drug than, say, a 250-pound male. And how do you make sure that each patient gets the correct amount of a substance? You're going to do some math with the concentration of that solution, right? But again, they don't use molarity because they don't give a crap about moles. They use something that's way more convenient for them, what's called a mass percent. All right, so our definition of mass percent is grams of solute divided by grams of solution times some factor F. Okay, and the value of F is different depending on what specific units are being used. The most common are what's called percent M over M, percent mass over mass. And then your value for F is just kind of what you would expect for percentages, 100. Right? So grams of solute divided by grams of solution times 100, that's what we call a percent mass over mass. All right? There are specific fields, in particular the one that comes to mind immediately is like environmental science, where they're really worried about, for example, water contamination, and they're worried about very, very tiny concentrations. So human beings are sensitive to extremely small concentrations of certain metal ions. So in particular, like arsenic and lead, absolutely terrible for us. We want to make sure that that stuff is not in our water supply, even in teeny, teeny, tiny quantities. So to use those teeny, teeny, tiny quantities, they have a different set of units they use, what's called ppm, or parts per million. And that is just a mass percent with that value of F instead of equaling 100, equaling a million. Parts per million, that value for F is a million. All right, and maybe they care about something even more teeny tiny dilute, ppbs, or parts per billion. And what do you think the value of F is in parts per billion? A billion. Okay, we can also say a million is the same thing as 10 to the 6. A billion is the same thing as 10 to the 9. Okay? And you can see that what the big difference of these units are, they just leave things in mass, right? They don't bother to convert to moles because, again, they don't care about moles. They just want to make sure that one patient gets 5 grams of aspirin and another patient gets 10. That's probably a crap ton of aspirin. Maybe not that much, but nonetheless, you get the idea, right? So this is how they keep track of their concentrations, but they just do so using this different set of units here. Okay, cool. So first things first, let's make sure that we can calculate. Actually, before we go through, we'll do an example problem here. But there's one more reason why using units of mass are very, very convenient. All right? And we're just going to do an example. I'll title this here in a second. Okay? But if you take, for example, 50 grams of, let's say, aspirin. We can't do that, actually. I lied. We're going to do 50 grams of ethanol. And you mix that with 100 grams of water. What you would have is 150 grams of solution. Okay, I'll be good with my sig fig. We'll make that 0 significant there. All right, but the whole point here, what I'm trying to illustrate is that mass is additive. 10 grams of this plus 10 grams of that is necessarily 20 grams, right? And if you think about it, that's because of where mass comes from. It's just a sum of the number of protons and neutrons, those subatomic particles. Well, those don't change when we make a mixture, okay? But what we like to use in the lab is volume, but volume's a little bit of a pain in the butt because it turns out that if you took 50 milliliters of ethanol and you were to combine that with 150 milliliters of H2O, 100, we'll keep it consistent, 100 milliliters of H2O, what volume would you expect to get? 150. Well, in fact, if you mix these two things together, you get more like 140 milliliters of solution. Okay? Volume, unlike mass, is not additive. All right, obviously we still use it in the lab. That's not to say that it's completely worthless, but it doesn't have this nice, neat property that mass does. Okay, so that makes these units of mass percent a little bit more convenient, right? Let's, again, our definition of mass percent was grams of solute over grams solution times some factor of F. But this denominator here, our grams of solution, what is contained within our solution? The solute, and what's the other part? The solvent. And since mass is additive, grams of solution is the same thing as saying grams of solute plus grams of solvent. Right? Our solution has these two components, the solute and the solvent, and because we're talking about the mass of our solution, we can find that mass by just adding the mass of those two components. Okay, we couldn't do the same thing if our units were in volume here. All right, cool. So let's just do an example problem here. What is the percent m over m if 34 grams of NaCl are dissolved in 164 grams of H2O? All right, calculate the concentration of this solution in our new units of percent mass over mass. All right, we're going to use our definition here of percent m over m, grams of solute divided by grams of solution times 100. Okay. How many grams of solute do I have in this problem? 34. My NaCl is my solute. And how many grams of solution do I have? Cool. All right. So my solute is that 34 grams of sodium chloride, but my denominator is grams of solution, and water is not the solution. The solution is when I mix the salt and the water together. So we have to do some math here. We got to take our 34 grams of the NaCl and add the 164 grams of H2O times 100. All right. This is the place where you got to be a little careful because we're adding here. And remember, our rules for sig figs are different for addition and subtraction than they are for multiplication and division. For addition and subtraction, it's all about the position. So my grams of solution here, I'm going to line them up. Let's just remind ourselves how we do this. We line it up at the decimals. So 34 grams NaCl plus the 164 grams of H2O. That'll give me my mass of my solution. Okay. So for each of my inputs, I have to mark that last sig fig. In this case, they're both in the same position. So I know I'm going to round my final answer to the ones place here. So 198 grams of solution here. $198 grams of solution. Okay, cool. So then I punch this into my calculator. I get 17.1717 repeating. Well, how many sig figs do I have in this answer? 2. My grams of solution had 3, but my grams of solute on my numerator only had 2. So we're going to round this to 2 sig figs. So just 17. And the units here are that percent m over m. Those are our units for this concentration. Yeah, the m over m is in parentheses. Final answer. Okay, cool. So, as we mentioned, the mass is additive, so my grams of solution are going to be my grams of solute plus grams of solvent. That gives me my grams solution. All right. Just note that now we have this operation addition. We don't do a ton of addition. We do a lot more multiplication division. So just don't forget that we have our different rules for our sig figs for addition subtraction. Okay. Cool. All right. Let's do another example here. What is concentration in ppm if 25 milligrams of iodine are combined with 260 grams of methanol? All right, so to be clear, what's our solute here? The I2, the iodine, and our solvent is this compound methanol. Methanol is an organic compound. You'll talk about that way more in organic chemistry, but just to remind us, this is what we used as our solvent when we conducted that zinc iodine lab, right? We took our iodine and we dissolved it in methanol. Cool. So you're going to take a second and calculate our concentration in ppm using the definition grams solute times grams solution. I'm sorry, divided by grams solution times a million, 10 to the 6. So we need grams of solute, and currently we have milligrams of solute. So we're going to have to do our metric prefix conversion. All right, 25 milligrams of I2. I'm going to convert that to grams using the fact that 1 milligram is 10 to the 3 grams. 10 to the negative 3 grams, I'm sorry. Okay. If you sort of use that 1 gram is 1,000 milligrams, that's great. That's also true. These are two equivalent fractions here. All right, but the 1 comes from our constants page, and that's what I told you to use, or taught you how to use. So I'm going to stick with that version here. All right, cool. So punch this into our calculator, 0.025 grams of that I2 solute. Okay. Now we need grams of solution. And we're starting out with our 0.025 grams of our solute. And we're going to add that 260 grams of solvent to give us our grams solution. Where's the last sig fig in that 0.025? What's the value? That 5. And where's the last sig fig in 260? That's 6. So where is my answer going to be rounded to? The tens place or the thousandths place? The one that's further to the left here. Boom. So when I do my math, 260.025 still only has 2 sig figs associated with it. All right, now am I going to round it when I go to do my next step? No, I'm still going to keep this whole number so that we can be good with our rounding error. I mean, honestly, in this case, it's very far away. Probably wouldn't make a huge difference, but for the sake of being good, 0.025 grams of our solute, I2, divided by that 260.025 grams of solution. I'm going to keep my sig fig marked so that I know my denominator only has 2. And now I'm going to multiply it by 1,000,000, 10 to the 6. I guess I should have done it. Oh, I see. Cool. All right, so we get 96.1446. All right, how many sig figs are we going to round this to? Just 2. So that'll be 96. And what are our units? ppm, parts per million, right? So those are our units here. Nope, just ppm. The percent means you're multiplying by 100. The ppm means you're multiplying by 1,000,000. They're both called mass percents because you're taking the ratio of the masses, but the value that you multiply it by is different. All right, cool. So just like when we were talking about molarity, the first thing we learned how to do was to calculate the molarity, but then we quickly moved on to actually using our molarity in our calculation here, okay? So same thing, we need to learn how to use these concentrations in our calculations. So what do I mean by that? Let's say, how many grams of NaCl or in 165 grams of a 34% M over M solution. All right, so I know I have 165 grams of solution. I need to know how many grams of solute there are in that solution given my concentration here. All right, so let's take a step back here and remind ourselves how we convert concentration into one of those conversion factors. All right. If a problem gave us something like 2.5 big M, we took that and we turned it into something that we could actually use in our math by splitting up those units. That big M is what units? Moles per liter, right? And so what we did was split it up into moles over liters, right? And then we used that as a conversion factor, okay? So 2.5 M turned into 2.5 moles in 1 liter. All right? So what we're going to see is something similar. We got our 2.5% M over M. We're going to take this and split it back up. Remember, that was grams solute over grams solution when we break up those units. All right? But our definition of percent M over M had this factor F in there, right? Grams of solute over grams solution times F. So importantly, when I'm turning this into something that I use in my math here, this isn't 2.5 grams of solute in 1 gram of solution. First of all, hopefully, we can see that that makes no sense at all. You can't have 2.5 grams of solute and then only 1 gram of solution, right? And again, it's because of that factor F. So this isn't 2.5 grams of solute in 1 gram of solution, but rather in 100 grams of solution, right? That factor F that we multiplied by 100 is going to appear in our denominator here. All right, so then by analogy, everybody take a second. 2.5 ppm, turn that into something that we can use in our math here. All right, that would be 2.5 grams of solute, not in 1 gram of solution, but in how many grams of solution? 1,000,000, yep, 10 to the 6, right? ppm means that there are 2.5 ppm means that there are 2.5 grams of solute in 1,000,000, 10 to the 6 grams of solution. Cool. All right, so given that, take a second and solve this problem for me. All right, so importantly, when I take this and I break it up here, turn it into a conversion factor. This is my 34 grams of sodium chloride in 100 grams of solution. That's what 34% M over M means. One more thing before we move on to make sure. Remember when we were talking about molarity and we split these units up, we said that all of our sig figs are in the numerator here. So this concentration has 2 sig figs, same over here. We said that the 1 on the bottom was exact, right? We see the exact same thing for our mass percents as well. All of the uncertainty is in that numerator, that 2.5. So this number also has 2 sig figs. The 100 in the denominator is considered to be exact. The 100 is not going to limit our sig figs. Cool. So then we're just going to start off. We have 165 grams of solution. Like any conversion factor, we can use it as is, or we can flip it upside down depending on what our units are. Do I want to use it as is or flip it? As is, because I want grams of solution to cancel. And leave me with units of grams sodium chloride. Cool, so punch this into our calculator, spits out 56.1, and again, our units are grams of solute, grams of NaCl. All right, am I done? No, all right, just like with our molarity calculations, you have a volume which is limited by sig figs as a measured value, but your concentrations are also measured values, right? So I'm limited by that 34. So we have a total of 56 grams of NaCl, rounded to the correct number of sig figs. Okay? All right, let's do one more example here. How many grams of solute are in a 12.5 pp. No, sorry. I want grams of solution are in a 12.5 ppb solution containing 0.5 grams of solute. right? So if I take my 0.5 grams of solute, am I going to multiply or divide by my concentration conversion factor here? Am I take it as is or flip it? Flip it. So I'm going to divide by that 12.5 grams of solute. All right, and do we get a big number or a little number? We get a really big number, right? Something like 4 times 10 to the 7 grams of solution are required to get only 0.5 grams of solute. Does that make sense given our concentration units here, right? Look at the definition. I mean, you could convince yourself by the math. You're multiplying by 10 to the 9 grams of solution, but yes, that's what a pp is. ppb is. It's for measuring very, very dilute substances. That 12.5 grams of solute is in a billion grams of solution, right? So there's only a teeny tiny amount of solute in that solution there. Cool. All right, so these units of concentration, these are the ones that are used primarily outside of chemistry. You'll see them in chemistry sometimes where it's convenient, but again, we like to default to those units of molarity because that's how we keep track of chemical reactions, is in units of moles. All right. Now I just want to take a second and review our reaction knowledge here. We did a lot over the past few weeks talking about chemical reactions. Let's just kind of take a second and take stock of all the different, I feel like they kind of blend together, mush together a little bit. Let's take a second to just lay out what it is that we learned over these past few weeks with regards to our chemical reactions. Okay? So the very first thing we did was I said, here's a chemical equation, categorize it for me, right? We learned about these different categories of these chemical reactions. All right, so what were some of those categories? Can anybody remember any of them? So we had a synthesis. What else? Single replacement. Any others? Combustion. Double replacement, double displacement. It doesn't matter, you'll hear it both. You'll hear both double displacement and replacement. We got one more. Decomposition, absolutely. Cool. Okay. And then last class, we kind of focused in on what category of reactions? Redox reactions. Now, importantly, many of these classes of reactions are also redox reactions. So to be clear, by redox reactions, these were reactions where electrons were exchanged. And which one did we highlight is a redox reaction here? The single replacement. We also did some examples of synthesis reactions that were redox reactions. Combustion reactions are redox reactions. Decomposition reactions are usually redox reactions. So all of these fall into that category. For synthesis and decomposition, I'm going to say sometimes because I'm sure there's an example out there somewhere where that's not the case, but I can't think of one off the top of my head. Okay? Notably, double displacement are not combustion reactions. All right, but nonetheless, all of these are reactions where electrons are being exchanged here. Okay, so first thing is, given a chemical equation, we should be able to throw it into one of these 5 bins here. All right, and then we took these categories, or at least some of them, and we kind of did a deep dive, right? So the first one that we really talked about in detail were these combustion reactions. These were the first ones that we should be able to predict our chemical equations for. All right, we started out a few weeks ago with me being like, here's a chemical equation, just trust me. And then we kind of graduated to, oh, you can write your own chemical equation for this particular category of reaction. All right, and that's because they all follow the same basic format. You have some hydrocarbon plus what? Not water. What's on the reactant side? Oxygen. And that will give you water vapor specifically, and what other product? CO2. Cool, so this was the first one that we can sort of predict our chemical equations for, our combustion reactions. And then we highlighted double displacement reactions. These were also ones where we learned how to predict the chemical equations for two particular classes of these double displacement reactions: precipitation and acid-base. All right, these precipitation reactions, this is where we mix two aqueous solutions and we get a solid product. All right, in order to predict the formula for these products, I guess we could say we get a solid product and an aqueous product. To predict our product formula, we just used that double displacement scheme, right? We swapped those two things out front, swapped those two cations, and then importantly, what did we have to do for our product side here to get our state of matters correct? The solubility table, right? So these are the ones, these reactions here are where we look up our products on our solubility table. All right, acid-base reactions are also mixing two aqueous solutions, but they're special aqueous solutions. One of them is considered an acid, the other one is a base, and an acid plus a base will give us what product? A salt and water, awesome. All right, and that salt is usually an aqueous salt. We'd have to be good and look it up on our solubility table to be sure. Okay, but yes, I always get that. Importantly, for an acid-base reaction, you always get that liquid water product. All right, and then we started out this week by talking about single replacement reactions. Okay. There we started out with what I'm just going to call these simple ones, where we had a metal plus an aqueous solution, and we could predict the products as another metal and aqueous solution by following that single replacement scheme. All right, but then we kind of used these to illustrate that broader class of reactions. I guess we can just note, again, we learned how to predict our chemical equations. right, but then we learned, we use this to introduce this broader class of reaction, these redox reactions. And single replacement is a type of redox reaction, as are combustion, as we've said, but nonetheless, I'm going to sort of set this aside as its own category, because what we learned how to do is some new skills with these redox reactions. Okay? First of all, we learned how to calculate what for our each element in our reactant side and our product side in these redox reactions. Well, yeah, but it wasn't quite charge. It's very similar to charge, analogous to charge, but something that extends to covalent compounds as well. The what number? Oxidation number, right? So the first thing we learned how to do here is to calculate those oxidation numbers. Kind of like charge, but not quite the same thing because it applies to covalent compounds as well. All right, and we use that to assign an element as being oxidized and reduced. And then we also introduced those terms oxidizing agent and reducing agent. All right, so that was our first skill that we learned how to do last class. And then we had even more fun with these redox reactions. We didn't stop there, right? We learned how to balance these redox reactions. And we learned that they can't be balanced by our simple mass balancing. We instead need to split it up and balance by what we call half reaction. All right, this has this crucial step that was new of charge balancing. It's kind of the whole shtick of balancing by half reaction is you can keep track of the electrons being exchanged by adding in this charge balancing step. All right, and then we sort of threw a curveball by saying, all right, we should be able to balance under acidic conditions. This is where we assume H plus and H2O are present. We use that in our balancing to balance oxygens and hydrogens. And then where we left off was under basic conditions, where you assume that there's water and what else? OH, hydroxide. Cool. So just kind of wanted to, I feel like sometimes things can kind of smush together, blend together, right? So just to kind of lay out what it is that we learned how to do for each of these different categories of reaction. And where we left off last time with your worksheet was balancing under basic conditions. All right, so that's what we're going to end with today. We're just going to do another example of balancing under basic conditions. So we got a fully worked through example in our notes here. Cool. All right. So we're going to take iodide, combine it with that permanganate ion. This is going to create iodine. And manganese 4 oxide. Now, previously, the very first step that we did was create an oxidation number table, and that allowed us to say which element was being oxidized and which element was being reduced, okay? We're going to first break this up into these half reactions. I'm just going to call this half reaction 1, where my iodide ion is becoming solid iodine, and half reaction 2, where my permanganate is becoming that manganese 4 oxide, all right, and I'm going to show you how after we go through our balancing procedure, we can assign these as our oxidation and reduction half reaction. The way that I've sort of oriented these on the page is to just try to give me enough room, because I know I'm going to sort of need to write another line under here and another line under here, and they're going to get bigger and bigger and bigger. If you write really tiny, you can put these things next to each other. I have found that I write way too big and it gets way too messy. So I just kind of stagger them on the page to give myself plenty of room to balance these out. I think you may have found on your worksheet last time that things can get real messy real quick if you're not sort of careful about space management with these problems, right? So I'm just giving myself plenty of room to work out each of these balancing steps here by staggering these half reactions like this. Okay? And I'm going to throw up here, that sounded weird. I'm going to put up here our list of rules for balancing under basic conditions. All right, so that we can keep these in mind as you're going through. And then I'm going to give you guys a little bit of a head start, and then I'll go back and work through that example. All right. We already did step 1. We balanced our, we broke up our chemical equation into half reactions. So now you need to balance all elements other than oxygen and hydrogen, then go in and balance with the water and the hydrogen ions, and then add your hydroxide. All right, so I'm going to give you all a bit of a head start, and then we'll work through that together. let's do this. So we broke it up into these two half reactions, right? Check, check. Cool. So the next step is to balance anything that isn't oxygen or hydrogen. Do I have anything that isn't oxygen or hydrogen in this equation here? Yes, my iodines. Are they balanced? No, I do not have the same number of iodides on both sides. I have 2 over here and only 1 over here. So I need to put a 2, coefficient of 2, on my reactant side. Down here, what are my other than oxygen and hydrogen element? The manganese. And are my manganeses balanced? All right, cool. Check, check. I got 1 on each side. I'm going to clean this up, which is going to bother me. Cool. All right, so now we're going to balance the oxygens with water. Do I have any oxygens to balance over here? No. Next step is to balance hydrogens with H+. Do I have any hydrogens to balance? No. Cool. So I can go to just the next step, which is that charge balancing step. Okay. What is the net charge of these 2 iodide ions over here on the left side? -2. And what about my iodine molecule over here on the right side? 0. That is neutral. So I need to charge balance, but the only thing I can do is add electrons. So which side am I going to add electrons to, left or right? The right side. So 2 electrons. Now if I recalculate my net charge over here on the left-hand side, or on the right-hand side rather, it matches the left-hand side, -2 and -2. Cool. So this half reaction here is now charge balanced. Okay, go over here. All right. I got to balance my oxygens by adding water. Okay, I have 4 oxygens on my reactant side and only 2 on my product side. So that means I need to add 2 waters so that my oxygens are all balanced out. Okay. Now, great, my oxygens are balanced, but I just introduced this new problem here of now I have these hydrogens that are unbalanced, and we balance those hydrogens by adding H+. Okay? Notice that in our rules for acidic conditions here, for basic conditions here, we still have to do step 4 where we balance with H+. We've added a new step in between 4 and 5, but that doesn't mean you skip step 4. If you tried to just balance with hydroxide, you would notice that you threw everything out of whack here, right? We're still going to go through step 4 so that we can get, this is just like kind of a bookkeeping trick here to make sure that everything is nice and neat and balanced. All right, so I'm going to add how many hydrogen ions to the left? 4. And those are AQ. Cool. So now I'm going to do that added step where I'm going to add hydroxide to cancel out. Remember, an acidic solution has a bunch of H+ floating around, but a basic solution has hydroxide. And to be clear, what we're going to use is we're going to take advantage of the fact that a hydrogen ion plus a hydroxide ion gets converted to water. So I'm going to add just as many hydroxide ions as I need to cancel out all of those hydrogen ions there. So I'm going to add 4 hydroxide ions. Okay, but if we look back here at our rules for basic conditions, it says that we need to add these hydroxide ions to both sides of our chemical equation. All right, so why am I adding it to both sides? Well, if I add it just to one side, it's going to throw off all of that balancing work that I did up until this point, right? So in order to keep this thing nice and balanced, I'm going to add to one side, and I'm going to add the exact same thing to the other side. Those 4 hydroxide ions get added to both sides. Okay, so now let's simplify things a little bit. these 4 hydroxides and these 4 hydrogen ions are going to combine to make what? 4 waters. All right, and then just because I want to save myself some writing, I can simplify this even further. What else can I do? The waters, right? So I have water on both sides of my chemical equation. You could have saved this step for the very end, but it will just kind of simplify things and make it look less busy. I have 4 waters over here, but I have 2 on my product side, right? So I can get rid of these 2 and just subtract 2 from this total. So at the end of the day here, my other half reaction is 2 H2Os plus that permanganate ion gives us that solid manganese oxide and 4 hydroxide ions. All right, so we can see that the net effect of adding that hydroxide ion step is that now in my half reaction, I don't have any H pluses left over. I just have those OH minus ions. And then what do we do after this step? The charge balancing. Awesome. All right. So my net charge over here on my reactant side is the 0 from my 2 waters plus that -1 charge on that permanganate ion. So a total of -1 on the left-hand side. All right, what's the charge on that manganese oxide? Neutral. There's nothing written up here, so it must be neutral. But now I have 4 hydroxide ions, each with a -1 charge. So that gives me a total amount of negative charge of -4. All right, so then where am I going to add my electrons to, the left or the right? The left. I can only bring these numbers down by adding negatively charged electrons. So I'm going to add 3 over here on the left-hand side. And now when I retotal everything up, I'll have that net of -4, matching my right-hand side. Okay, I had told you this acronym LEO, losing electrons, is oxidation. There's another one that I heard that I kind of had forgotten about, which is oil rig. All right, and this stands for oxidation is losing and reduction is gaining. Losing what? Gaining what? What are we talking about here? Electrons. Okay, so we split up these 2 half reactions, but we haven't assigned them yet. Let's take a look back at our mass balanced, charge balanced half reaction here. Is this half reaction a reaction where the element is losing electrons or gaining electrons? My electrons are over here on the product side. So this is a half reaction where my iodine is losing electrons. And losing electrons is which one? Oxidation. Oxidation is losing. Right? So my fact that my electrons are on my product side here means that this is my oxidation half reaction. And if I go here, let me get rid of all this ugliness so we can see it a little bit more clearly. In this half reaction, the electrons are on my reactant side. So this is my reduction half reaction, where that manganese is gaining those 3 electrons. All right, cool. So now we're going to take our reduction half reaction. I'm going to copy my oxidation half reaction down here. Okay? And the last step is we want to sum these up. But we're going to sum them up in such a way that we cancel those electrons from both sides. All right? If I just add them together as is, my electrons won't cancel. I don't have the same number on both sides. I need the same number on both sides, and I don't want to just increase this to a 3 over here because that'll throw off my charge balancing. So instead, I'm going to take the whole thing and multiply it by 3, and my whole reduction half reaction, and multiply that by 2. All right, so the sum of these two reactions here, let's see if I can write small enough to fit it all in, is my 2 iodide ions plus these 3 electrons plus 2 waters. Oh, no, I'm not. What am I doing wrong? Yeah, I'm not adjusting my coefficients here. All right, start it over. I got 6 iodide ions and 6 electrons. We'll make 4 waters and 2 permanganates. These will react to form 3 iodine molecules. We got my 6 electrons. Two of those manganese oxides. I'm gonna squeeze it in here. And lastly, those 8 hydroxides. All right, which I know was everybody's first guess. As soon as they saw that unbalanced chemical equation, you knew exactly what it was going to be, right? No, okay, trust the process. You got to go through that step-by-step process, right? You get this big, ugly thing at the end. We're going to cancel everything that appears on both sides here. I actually sort of canceled halfway through those waters, but I still get to cancel what from this chemical equation? Those electrons. Cool. All right, so my balanced redox equation here under basic conditions. Oops. Boom. All right, we have some waters left over in this equation because they're helping balance our oxygens, and some hydroxides. That's because this reaction took place on an aqueous basic solution here. Okay, and just to be clear, this was our balancing by half reactions under basic conditions. This was this step-by-step process we followed here. Cool. Break. Awesome. All right. Yeah, so for today's lab,